there have been so many times that I have gone to PCB West, and it has given me this little bit of information that was crucial to make this project work. And it was right in time before I got this project done too. So, for example, I was working on a power supply, and I had done so much signal integrity layout, but not as much power layout. And so they said, here's how to make power layouts work. I took a bunch of power supply classes from Rick Hartley and so forth. And I'm like, oh yeah, that makes sense now. And so I go back and I changed that thing, and it made the project work. I was building this 160 watt power supply. I'm like, now it works. Now it does right. And now I wish I had known this the first time. It would have saved me 2 months of work.
Hello, everyone. Welcome to the Altium On Track podcast. I'm your host, Zach Peterson. As you can see, I am still in our temporary podcast recording studio as we make the move to a new podcast recording studio. So I hope you will bear with me for a couple of episodes. Today, I'm going to be talking with Keven Coates, Senior Electrical Engineer at Novium Designs. I met Keven, I think 4 or 5 years ago at PCB West. And for those of you who have attended PCB West, you have probably recognized Keven's face. So I'm very happy to talk to Keven today because he has some very interesting topics coming up at this year's PCB West. Keven, thanks so much for being here today.
Yeah, thanks for having me. This is going to be great.
Absolutely, yeah. I feel like I should have had you on earlier, but better late than never, right?
Right.
So if you could, since you are a new guest, just give us a bit of an overview about your background and how you got started in electronics.
Sure. Yeah, I'm one of those people who I've been around for a while, but I started at a young age. I have always been a builder. Now they call them makers, which I think is awesome. I love the maker movement. Man, I wish that would have been a thing when I was a kid. When I was a kid, I think they just called me weird. But I loved building things even as an 8 and 9-year-old. I loved to build little model cars and stuff like that. And I wanted to make them remote control. And I wanted to do mechanical things, but I didn't really have the cool tools to do the mechanical stuff. My father was a mechanical engineer. And but he also knew electronics. He taught himself electronics, and he introduced me to electronics. And so while I didn't have the cool tools, I had a soldering iron. So I thought, hey, all I need is a soldering iron. I can make my own circuit boards with just a copper clad and some ferric ammonium citrate and so Sharpie marker. That's the way we do it back in the old days. And it worked out pretty well. So I started building circuits and got into audio a little bit, modified some car stereos, did stuff like that. And then I got into when I was starting college when microcontrollers became cheap and available. You probably remember the Motorola HC11. Man, that was a long time ago. Maybe it's before your time, but it was a neat little board, and it was $80, which was pretty cheap for a board like that, even though it was a lot of money back then. And that's when my embedded processor kind of love started to take off. I started realizing, hey, we can actually measure real world stuff and control real world stuff with this kind of electronics. So that's been kind of my staple since 31 years ago. It's all been embedded microcontroller. I was with TI for 20 years, got into digital signal processing, some memory stuff, some battery stuff, and that's been kind of my path.
So you used to work at Texas Instruments. Were you actually doing chip design? Were you just doing the eval board design? What were you doing over at Texas Instruments?
Well, it's funny because I think it's kind of true at most tech companies. When you have a job at a tech company, it changes a lot because tech changes a lot. So I moved jobs about every 5 years within TI, sometimes every 2 years. I started out in flash memory, actually, back when the flash memory was a new thing, non-volatile memory, the precursor to SD cards. And then I got into the more interesting stuff, got into portable audio, which is MP3 back when that was new. And then I did portable audio and video, and then I got into auto infotainment and stuff like that. So I was doing a tiny bit of chip design, a lot more package design, because TI, as a lot of silicon companies, don't really understand the PCB. they only make chips, and they make really nice chips, and they want to make them as small and as cheap as possible for both you and for them. But they don't understand that a 0.4 millimeter pitch BGA isn't going to make anybody happy except for the cell phone people. So I was kind of the liaison between package design and PCB knowledge for our customers. In fact, I did a ton of example layouts. I pioneered something called via channel that TI still uses on some of their big processors. And that enabled us to do like huge chips, 1031 pins on 0.65 millimeter pitch. And we were able to escape that in only 2 signal layers because there was depopulated balls in a kind of a radial pattern. So I did a lot of that. I did a ton of eval boards. That was really my bread and butter, the package design and the eval boards. So I did a ton of systems, mostly a jack of all trades kind of. This is a new chip, and this is everything it can do.
Now, you mentioned something that I think older folks in the, or more experienced folks, I should say, in the industry are well aware of, which is that silicon companies aren't always the best at printed circuit board design. I think I'm being nice here when I say that. I've used much harsher comments in some of my seminars, so I'm very aware of that. I still see young people seeing, application notes or seeing the dev board or seeing, a layout example in a data sheet and kind of, taking it as gospel.
Oh, yeah.
What would you say is the problem with that?
Oh, my gosh. I
have my own thoughts, but as the guy who used to work for the silicon company, I really want to hear what you say.
Well, let me tell you, one of my first writing jobs at TI was data sheets, and I could write pretty much whatever I wanted to, and it was reviewed by the technical writers and by a few technical people, but not as much as you'd think. And PCBs were, it's silicon companies, they really concentrate on the silicon. They do not understand PCBs. They do not understand copper features, copper spaces, traces. They don't understand what drives cost. In fact, that was a huge part of my job as in the later years. I went to Taiwan actually many times to talk to the tier 1, 2, and 3 PCB makers, ask them what really drove cost in the non-HDI designs. And so I learned that early on, and I told that to TI. I said, hey, you can't just expect everybody to do HDI design. A lot of people don't like that. It's going to double the cost of their boards. And they really had no understanding of that at all. So, and then later on, I got on a committee for packages because they weren't even designing. I might get in trouble with TI here, but I don't work for them anymore. They didn't understand IPC. They didn't understand ball pad sizing. So they were actually putting out white papers that were wrong. So they had just completely incorrect information. And so while they did do some tests for BGA board adhesion, they did the screwdriver test, later on some packages. Most of them were kind of untested. And so they formed a committee, and I was part of the committee, and they had to update like 20,000 footprints. And I think they're still in the process of that to try and get them to comply with the IPC specs. So, as Rick Hartley would say, don't trust the data sheet in terms of PCB layout unless it is proven, and it is rarely proven.
Now, I agree with you. You should always be a little skeptical of the data sheet. I see some interesting practices that sometimes don't have a justification explained in the data sheet.
Right.
Sometimes the justification is in the data sheet. And then sometimes they just take the dev board layout and they're just like, here's your layout. This is what you should do.
Yeah.
And I think when you do the dev board, a lot of times it's fine, especially like with power products, because you're probably testing it with a DC load, right? It's a dev board, right? Does the circuit work?
I can tell you, because I did dozens of eval boards. I mean, dozens. And that was my job. And so let me tell you how those layouts, they come up with those layouts by going to the PCB shop that we generally go to, it was Spectrum Digital back in the day and some of the others, and saying, here, lay this out. The TI people don't lay it out, and the silicon companies don't lay it out. They they don't have the understanding to do that in general, so they have somebody else do it. Now, of course, it's different if you're doing something like an AMD processor. They get really into their layout, like with Dan Beaker. But for the most part, for like LDOs and BGAs that are just simple processors and things, they don't do that. And that's why they do a bunch of things that, like you said, people take them as gospel, and they took my eval boards as gospel all the time. And I'm telling them, I'm like, this board has not been FCC tested. This board has not been in a product. I don't know if this is a great design or not. It's an example. That's what it's meant to be, an example. It's not meant to be gospel.
Sure, yeah. And then this is where you get people kind of copying and pasting, whether it's a recommendation or the layout, directly out of the data sheet into their design software. And they're like, yeah, I got it. We took it from the data sheet. There shouldn't be a problem. Mm-hmm. But I guess the caveat to that is, if you were to do something different from the data sheet, can the silicon company guarantee that it won't work? And if the answer is no, then you're free to do what you need to do with that component rather than just blindly following the data sheet.
Oh, yeah. We had, for a while, it was in voice band modems, which tells you how long ago that was. But we had customers like Logitech and Best Data and Cardinal and Hayes and all those. And we had customers that really wanted to make the PCB as cheap as possible. And we told them, I said, we really need 4 layers for this design. There needs to be a ground plane, needs to be a power plane, 2 signal layers at minimum. And they said, we think we can do it in 2. And we told them, no, I don't think you can. You don't understand. This is analog electronics. It's very sensitive. And they said, we think we can. And so they tried it. I think it was Cardinal. I don't think they're in business anymore. And they said, man, we're really having trouble with this design. Can we ship it to you? And so they did. And our tech actually put a foil layer on the outside of the PCB and grounded it, and everything worked. And we told him, we told you needed 4 layers for this. This proves it.
Yeah. It's always simple stuff like that, right? I feel like a lot of the PCB changes that are needed to get a design like that working, like 80% of the problems are solved by relatively simple changes if you have enough experience to see it.
Absolutely. And I think, going to PCB West is a great example of, if you get that kind of knowledge, you get a gut level feel for the signal integrity, how those return paths flow, then you're going to be better than most of, for example, in the TI data sheets, they always show that they separate the digital and analog grounds. And a lot of people think that's because they have to, or because it's good practice. Well, it is because they have to, and they have to because people demand it. Because there's a lot of people who think that analog and digital grounds should be separated, and they won't buy a product unless it is. But when I was designing the PCB in the later time, when I knew enough about doing it, I would just connect them directly on the same plane. And people are like, well, why didn't you separate them? Like, because it's not a good idea to separate the analog and digital grounds in most instances. There's tons of YouTube videos about that, with Rick Hartley and a bunch of others. You've probably done one too. So that's a good example why you see these things done in the data sheet, and sometimes they're done in the data sheet because people demand that it's a possibility. Doesn't mean it's a good idea.
Yeah, that's funny, because I had a discussion with Dan Beaker while I was trying to walk up to my hotel room at PCB West, and he was sitting down there in the lobby having a drink, I think. And of course, he and I got into this conversation. But you mentioned that they show the pins separated to different names, right? Like primary ground and secondary ground, or
right.
Analog ground and D ground. Mm-hmm. And I have actually seen this on Texas Instruments ADCs, and they do name the pins differently. One reason for doing that is for example, testing. Mm-hmm. But on the very next page, after you see the pin diagram, they say right there in one sentence, connect the pins with a single plane, and people still don't follow it.
Oh yeah, all the time. And it's the data sheet. There's a lot of really great things in the data sheet, but sometimes it's in the really fine print.
Yeah.
It takes a long time to get into that. So, for example, the other day I had a guy who said We really, this LDO is a great design, and it handles this much power, and then we ran this much, it says 100 milliamps, and I'm saying, okay, that comes with a lot of caveats. It says 100 milliamps, but it's this big. If you're dropping 12 volts to 5 volts, it's not going to do 100 milliamps. It's going to do 100 milliamps from 5.5 volts to 5 volts.
Yeah.
So
Yeah.
those are the caveats you find out if you learn how to read the data sheet well enough. But man, sometimes it's so critical, these little details.
Absolutely. Absolutely. So I think we've found a good time to segue into PCB West because we've both brought up something about the conference. Obviously, PCB West coming up this year, end of September, beginning of October. You're going to be there. I'm going to be there. Rick Hartley, you mentioned, is going to be there. Susie Webb. We've got some other folks who are there every year. And I wanted to talk to you because I think you have some interesting topics that you're going to be talking about at PCB West. So if you could, can you run over the topics that you're going to be talking about during the conference?
Absolutely, I would love to. Yeah, so I'm teaching 4 classes this year. Kind of a light load, but I've got a half day of signal integrity basics with some examples in PCB layout. It's a beginner's class. It's kind of a signal integrity 101. It's a great refresher course if you haven't had one for a while. I don't know about you, but I took signal integrity the first time back in Howard Johnson's days. So that was way back in the day, and he was great. But I had to take it, oh man, I don't know, 5 times at least just to get an idea of how it all worked together. Because you have these, it's like drinking from a fire hose at first. You have these thoughts, where do these thoughts fit in? How do I get these things together? And so, in my opinion, you really have to take these 101 classes over and over until you have a gut level feel for how it all goes together, because otherwise, you just don't know. And so this class is kind of taught from a different perspective. You've got Rick Hartley's classes, which are fantastic. And, he and I are teaching the same thing, just from a different angle. And I think it takes a couple of different angles to try and kind of see the thing. When you look at something from one angle, it helps to see it from another angle as well.
I would, if I could jump in, I would absolutely agree with that because it makes me think back to my university days, right? And you would get introduced to same or similar topics from different professors, but because they're coming at it from, these slightly different perspectives, you can actually see where the mesh happens. And then you get a lot of context on the stuff that they're talking about rather than just taking, what the one guy said as gospel and just repeating it. So I advocate for exactly what you said, which is to, get it from a couple different angles and it'll really help you understand it at a deep level.
Yeah, it's really true. I took every 101 class I could take. I took it from Rick, from Howard Johnson a bunch of times. I must have sat in every one of Rick's classes 5 or 6 times. And it just helps. It really helps to hear it over and over and hear it from different perspectives. And people's perspective changes over years and years too. So that's helpful.
So you have a couple other topics as well. I know signal integrity is, of course, a popular one. You also have something on thermal, if I'm correct?
Yeah, I have a half-day class on PCB heat management. Talk about, everything from LEDs to MOSFETs, fans, heat sinking, heat pipes, thermal interface material, basic thermal modeling. It goes through a lot of things. The nice thing about thermal modeling is it's really not as hard as people think it is, and you can really gain a lot of insight from just a few simple equations. I wouldn't even call them equations, more like algebra. Then we talk about things like tools, thermal imagers, they're fantastic, but there are some caveats on that. You can't shoot shiny metal, or it just basically tells you the reflection temperature, even if it's 700 degrees. Some things about airflow measurement. It's a beginner's class, but it's super helpful because heat management is just widely misunderstood.
Yeah, and it's kind of a product level thing too, because you can have a hot circuit board, but if you design the strategy around the hot circuit board and you design the enclosure appropriately, it's actually possible to get a product that is not going to burn itself alive.
Right, exactly. Yeah, it's all about spreading the heat out. That's thermal management in a nutshell. In one sentence, it's spreading the heat out. Because if you have one part putting out half a watt and it's 1 millimeter by 1 millimeter, that thing is going to turn into a fiery fireball. But if you have half a watt spread over, a couple square inches, no big deal. It's not a problem at all.
I see. Yeah, that's a good point. Do you also go into? Yeah, I think you mentioned thermal interface materials, so I'm going to assume you go into like heat sinking, whether it's
Yeah.
with like an extruded heat sink or possibly even using the enclosure as a heat sink.
Yes. Yes, absolutely. Yeah. And I talk about different ways to model that and different ways to test that. Heat sinking, how to choose heat sinks, whether you need a fan, whether you don't need a fan, uh, and basically all the simple equations that go along with that stuff.
So if someone's going to be designing something, they know it's going to have a high thermal load, and I've had to do several of these designs. If they know they're going to have that kind of high thermal load, they probably have to put it through some kind of testing, but like long term reliability testing, right? Not just measure the temperature once and call it a day.
Hmm.
Do you talk about that at all?
A little bit. So basically, everything is about temperature, right? So every 10 degrees C reduction in temperature doubles the life of a product in general. And that's not a hard and fast rule, but it's kind of a rule of thumb. So it's based on a certain equation, chemistry, and so forth, because you don't really know how every chip is going to, or how every capacitor is going to degrade. But in general, from a chemistry perspective, that's how things degrade. So it's great to know that. And you can actually talk to semiconductor companies. Like in my class, I talk about TI DSPs are in fuel pumps. So when you go pump gas, you got that color screen and the color screen showing commercials and stuff like that. Long ago, Gilbarco came and said, hey, we want this DSP to last for 70,000 hours. What temperature do we need to hit to make that happen? And they went and did some calculations and they said, okay, if you keep this processor at 70 degrees C or lower, it should last 70,000 hours. So it's pretty amazing. I talk a little bit about L10 and half half-life kind of thing. What's that? I can't remember the term right away, but we cover that real briefly. But yeah, it's all about keeping things cool.
Yeah, yeah, I would agree. Some of the other stuff that you'll be talking about in different seminars.
Hmm.
As I recall, there's also something on DFM, DFA.
Hmm. Yeah, I've got a 2-hour class on avoiding assembly pitfalls. It's funny because there's so much to cover on DFM and DFA, and everybody approaches it from a circuit board perspective, and that's great. But I approach it from a kind of an overall perspective, kind of how do you work with your assembly house to get the first run yields up? And I've heard it say that 60% yield on a first run prototype is acceptable. And I've had that experience too, and it's terrible. But how can we do better? We can do better by addressing things that we know are going to be a problem before they come up. So that's what this class talks about. It talks about how you can choose an assembly shop. It talks about how they're going to do certain things like washing if your product needs washing, and things that are going to affect whether it works the first time or not, and how you can make that better.
So, what are some of the DFM, DFA common mistakes that you've seen over your time, let's say working at Texas Instruments or possibly working at Novium Designs?
Yeah, actually, I was liaison from the engineering to the assembly shop in a company called Geospace Technologies I worked for 7 years. So that was my biggest eye opener, I think, there, because I had an in-house assembly shop, and I was the guy who talked to them. And the biggest problem that I had there, and actually I think back in the TI days as well, was diodes. They were always putting those things in backwards. And you look at the footprints and you're like, well, is it clear? Because these assembly people are not going to go look at the schematic. They're not going to see,
Right.
well, this connects to this. They're going to look at that footprint and they're going to see, where's the bar? Where's the dot? Where's the little diode symbol? How am I going to put that on there? And if it's not clear, then they may make a mistake. And you get into things like LEDs, and it's way worse. And the through-hole LEDs are the worst because some of them are just round, and the only thing that polarizes them is the length of the leads. And if they were not smart and they cut off all the leads before they put them on the PCB, well, 50% of those things are going to be wrong. So diodes are the worst thing, I think, in general. But another thing is putting components too close to the edge of the board is a big deal, especially in V-scored boards, because when you have that V-score, that big knife is going to come along, that roller, and it's going to roll right through that V-score, and it puts an immense amount of strain on the edge of that board. If you put big 1206 capacitors or something like that on the edge of that board, 1210, they're going to crack, and they're going to short, and they're going to be open, or something that's going to be really bad. Been there, done that, back when I was younger and dumber.
I think you just came up with a new DFX acronym, which is DFDP, Design for Depanelization.
That's true, yeah, and that's a huge one. Oh my gosh, I can't even remember how many problems I had with depanelization, because the V-score thing is, best case, it's a lot of stress. If you get that wheel just a little bit offset, it's a ton of stress. And that wheel gets offset a lot because those assembly people are not over there going, they're down there, rah! I mean, they want that thing depanelized, and they want it depanelized now.
They've got a ton of boards to run through, so of course they're gonna, they're not gonna dilly-dally.
Yeah, exactly. They're there for speed and accuracy. They're like, if this thing cuts, I'm good. And I've seen them cut right through capacitors.
Oh wow! Yeah, I guess you wouldn't assume that someone would do that with a V-score knife, I guess, right? Because the descriptions I've heard of V-score knives, and I've never used one, but the descriptions I've heard is that they're like pizza rollers.
They are, but they have immense pressure, and ceramic things crack really easy.
Sure. I guess you don't assume a pizza roller to produce that level of stress, but it makes total sense.
They're like a pizza roller with about 2,000 pounds of force.
Yeah, that's more than enough to crack a capacitor for sure. So what about mouse bites though? What about mouse bites near components?
Those are significantly better. And of course, if you route it, that's better too. If you can route as much as possible. If you can get an assembly shop that does laser, that's even better, because then there's no stress. So that's fantastic. But that's a new thing, and not a lot of assembly shops have that yet.
I see. So then what about some of the DFM problems, like, for example, from the fabrication perspective?
Yeah, so, let's see, fabrication. You're talking about depanelization, stuff like that?
Well, more like, component placement, routing, those kinds of issues, because I think people will design something with a certain idea in their mind of what the constraints can be with their manufacturer, and then all of a sudden they get no bid and they're not sure why.
That sounds like the last product I just worked on.
Yeah.
And it's sad, because I've been telling them, what you need to do is you set up your Altium so that you have default clearances. And to get those default clearances, you should be working with your assembly shop, because they're the ones, the PCB fabricators, they're the ones who are going to be saying, is a 10 mil drill going to be used? Is a 12 mil drill going to be used? What is your finished hole size? What is your clearance? How is your registration going to work? All that stuff is up to your assembly shop. And when you talk about North American assembly shops, they're all very different, because they all have their niche that they do. So it's not like if you go to a tier 1 shop in Taiwan, they're all pretty much the same. They all do kind of the same clearances in general, but the ones in America are not like that. So if you're trying to get prototypes built here, you really need to work with your assembly shop up front. You need to have your clearances in Altium before you start the design, because it is next to impossible to go back and fix it after you're done. Yeah,
I think you can. It's possible, but how long of a design rule error list do you have to work through to do it? I think is another question you have to ask.
Exactly. Last design I worked on had vias that were just a little too small, and they said, okay, you really need that annular ring to be a little bit bigger. Well, dang, to put another 2 mils on the annular ring in every area, oh my gosh, it's going to take me 100 hours.
Yeah. And then on top of that, right, and this is actually something I've seen in designs that were going to be intended for class 3. And of course, the client didn't say anything until the very end. So we design it class 2 and pretty aggressive on the clearances, but then they say, oh no, we want to do this class 3. So you need to beef up the via pads so that there's enough annular ring. Well, what happens there? Yeah. Clearance violations, right? All over the place.
Oh, you might as well just start again. I mean, it's probably better to start again because, and sadly, I think every class 3 shop does the same thing. They're like, we want a class 3 design, but we don't want to pay for it in clearances or density. It's impossible. So I don't know if I've ever seen a true class 3 design.
That's really interesting too. And for those that are listening, class 3 is, of course, like military, aerospace, those kinds of things where a failure could potentially cost human life. And so there are
Yeah.
these little things that we do in the PCB to make sure that we ensure just that little bit of additional reliability.
Mm-hmm.
And then, of course, it all has to get qualified in fab and assembly. With class 3, another thing that with high density is if you do mess up or nobody tells you that it's going to be class 3 until the very end, and then you have these vias, the other solution that I'm going to bring up, which is, oh, well, can't we just reduce the via diameter?
Mm.
Sometimes
Yeah.
it's no, right? I mean, if you start with a 10 mil via, yeah, okay, you can go to an 8 mil via, but
Mm-hmm.
going from 8 to 6, what's the problem there?
Yeah. And the board shops always, if you want to stack the boards, which every board shop wants to stack the boards to reduce their assembly time because time is money, right? So if you want to stack the boards, you don't expect an 8 mil drill. That's not going to happen. It's going to be a 10 mil drill or 12 mil drill, which means your annular ring's got to be bigger. Yeah. So every time you try and address these things, when you're done with the layout, it's going to be time or it's going to be money or it's going to be both.
Yeah. So I think everyone that is listening right now and is interested in some of these topics, they should go to PCBWest.com. They can see the schedule. Just Control F, Keven Coates, and you'll be able to skip past all the other people and go to the stuff that's important. But of course, one of the reasons that I think, we all go to PCB West, especially for, folks like yourself who are speaking and, I go there and speak too, is not just to hear ourselves talk, but also because we want to see both the show floor as well as other people who are going to be there. So my question to you is, what are you looking forward to seeing at PCB West this year?
Oh yeah, you hit it on the head there. I love to see, you really need to stay current in your job because tech changes all the time. And I will say, PCB clearances and things don't change as much as I wish they would, but you always have new materials, new stuff, like you have that UHDI class. I love the HDI classes. UHDI is especially interesting because there's a lot of neat stuff happening in that area. I love to see, Rick Hartley is always awesome, Susie Webb, Dan Beaker, got Thomas Chester, all sorts of awesome classes, Terry, and yeah, there's so many great teachers. I keep telling the people, because my work has to pay for, I mean, it'd be nice if they paid. I've gone myself before, but it'd be to sell the trip to my company. I'm like, well, there have been so many times that I have gone to PCB West and it has given me this little bit of information that was crucial to make this project work. And it was right in time before I got this project done too. So, for example, I was working on a power supply and I had done so much signal integrity layout, but not as much power layout. And so they said, here's how to make power layouts work. I took a bunch of power supply classes from Rick Hartley and so forth. And I'm like, oh yeah, that makes sense now. And so I go back and I changed that thing and it made the project work. I was building this 160 watt power supply. I'm like, now it works. Now it does right. And now I wish I had known this the first time. It would have saved me 2 months of work.
Yeah, absolutely.
Yeah, that's what I love. I love to see the board shops and I love to see the embedded capacitor people. And yeah, there's some great companies down there too to see what's new in soldering and stuff like that.
Yeah. Going to the show floor is always so much fun because it's, I mean, yeah, of course, you're seeing the manufacturers and the material suppliers and those kinds of folks. And, it's always nice to talk to some of those companies. And, sometimes you run into a company that might just, service you on your next project. But I think one thing that's really cool is it's such a great place for networking. And I can't tell you how many times I've run into somebody on the show floor just randomly, and it's like, oh, hey, like, and you get to, catch up with people that you know and haven't seen for a long time, and meet some other great people there who you probably should know.
Yeah, and it's awesome because they're so reachable. I mean, I don't know any teacher. The first time I went to PCB, let's see, I went to PCB Austin, which is forever ago. I don't think they've had one since then. And then I went to PCB East in Boston, and that was a really small one because of some weird conference stuff that was happening at the time. It was long before COVID. And the nice thing was, since it was so small, I got Rick and Susie to myself and Gary Ferrari. And man, I had lunch and dinner with them so many times, and it was just so great. All the teachers are so reachable, and they're happy to sit down with you and solve a few issues here and there if you need that. It's so great. The people are just so friendly and everything.
Yeah, 100% agree. And I guess that's kind of the benefit of being in like a smaller, I don't want to say niche industry because PCBs are in everything, but a definitely smaller industry like when we're in, because like you say, the important people or the people you learn from, you can literally walk right up to them and ask them questions.
Right. Yeah, I have people ask me questions after every class, and I love that because it's like, well, that means what I've taught them is something they needed, and it also means they have extra questions, which I love to answer because it just makes me feel, valuable, like my class was really useful. I personally enjoy it better when people come up to me after the class than if they just all take off. Maybe sometimes there's lunch and stuff, but I understand. But it's like, wow, I just feel so much more useful if the class was something they actually needed to hear. So
yeah.
nice.
Absolutely agree. Absolutely agree. Well, we're getting up here on time, but I want to thank you so much for being here today. Like I said earlier, we should have done this earlier. Haven't had a chance to do it. But I thank you very much for coming on here and talking about your upcoming sessions at PCB West.
Yeah, happy to do it. Great to be here.
Absolutely. And we'll have you back on again in the future.
Awesome.
For everyone that's out there listening, we've been talking with Keven Coates, Senior Electrical Engineer at Novium Designs. If you're watching on YouTube, make sure to hit the subscribe button, hit the like button. You'll be able to keep up with all of our podcast episodes and tutorials as they come out. And last but not least, don't stop learning, stay on track, and we'll see you next time. And hopefully we will all see you at PCB West. Thanks for watching, everybody.